Okay, so right, let me just quickly review what we have done so far in the class. So we talked about R as an ordered set and field. Then we have talked about sequences and limits. And then we talked about series. And then finally, we have talked about, and this is where we will continue today, we talked about metric spaces. And so the idea here is that we want to, there's a lot of things that from R that actually generalize and make sense. And some of those are sequences and limits, so they generalize from R to metric spaces. There are other things that don't generalize. Like it's not an order, a general metric space is not it doesn't necessarily come with an ordering, and it's not like a field. In particular, typically you can't sum elements, so a series doesn't make sense either, right? But these things here make sense in a metric space. And so let me just remind you what is a metric space. So a metric space is a set, so X is a set. And then there is a distance function. So this is a map from X cross X into R. And for each two pair of elements, X and Y, in X, you have that, let me make it a capital like X like this. For every two elements in this set, the distance between them should be positive, and it should be non-negative, and equal to 0. The distance between 2 points should be 0 if and only if these points are the same, right? And then it should be symmetric. So property 2 is that it should be metric. So it doesn't matter whether you go from X to Y or from Y to X. The distance is the same. Then, and the third, which is like the most non-trivial part, is the triangle inequality. So this here is symmetric. And the third property is that if you're looking at X, Y, and C, so you have 3 points, and you go from X to C, then it's certainly not further than if you first go from X to Y and then go from Y to C, right? So this should be less or equal to the distance from X to Y plus the distance from Y to C. And so this third property here is what's called the triangle inequality. So this here is the triangle inequality. Okay. Now, so that's what a metric space is. And again, the sort of canonical example. So the canonical example of a metric space is where you're taking X equal to the real numbers, and then for two real numbers, the distance between them is just where you're looking at the norm of the difference. Right, so this here is a nice distance, right? It's clearly non-negative. It's clearly equal to 0, if and only if X is equal to Y. It's clearly symmetric, And the triangle inequality is this inequality that we've used all the time. Right? The same, so this here is slightly more fancy version of the same, is where you're looking at R2. So the x here is R2. Or it could even be a general Rn. And then if you think about two elements in Rn, and you think about, say, x here as it's written as x1, x2, up to xn, where each of these xi's are in R, and there are n many of them, and likewise for y. And then the distance here, the natural distance, is where you're taking, this is what's called the Euclidean distance. It's given by Pythagoras. And so it's the square root of the sum of the squares. So x1 minus y1 squared plus x2 minus y2 squared plus, and then all the way up to xn minus yn squared. Right? And so you see that if n here is equal to 1, well, then each element is just a single element in R. And so then this thing here is really the same as that, right? Because it's the square of x minus y. It's the square of this distance, and then you take the square root, so it's the norm. Okay, so these here are, both of these is called the Euclidean, usually referred to as a Euclidean distance. So we looked at a few other examples, and I won't look at all of them again, but just two more. One is this with a box distance. And let me state it only in R2, but you could, just like this, you could state it in any Rn. So the space is R2, and the distance between two elements. So again, we write it like this, and we think about x as being x1, x2, where these are real numbers, y equal to y1, y2. And then this distance here is the sum of these distances. So it's this here plus x2 minus y2, like that. Right? And this is clearly, again, symmetric. It's clearly non-negative. It's clearly equal to 0 if and only if x and y are the same. And the triangle inequality, well, that just follows quite easily from the triangle inequality for this distance. Okay. Then there is one more example. I mean, there's other, but there's one other more example that is often useful to keep in mind. And this is the last one I will review. And so this is the continuous function. So if you take an interval, a and b are real numbers, and you're looking at the interval from a to b, where both endpoints are included, and then you look at the continuous function on this interval. And then if you have two elements, f and g, so these are continuous, each of them are continuous functions, then the distance between these two continuous functions is equal to the max over x, and then f of x minus g of x. Right, and so x here is in the interval from a to b. Right. And so this thing here, so this here was on the midterm, this particular example, And this thing here, that the max is achieved, is just like if you're looking at these two functions, then this is the difference between the two functions. So this is also continuous. And this means that the maximum at the minimum by the extreme value theorem is achieved on an interval of this form. Right? So this thing here is really achieved. And it's clearly non-negative. And it's easy to see that it has the other property of a metric space. Okay, so these are just the examples that we talked about. And I just wanted to remind you. And so then the question is, what generalizes from R? So we started with the class talking about R. And, so it was an ordered field, but a lot of the things we talked about for R, the subsequent things we talked about, sequences and limits, they, as we will see, make total sense in a general metric space and has important consequences, including to solve differential equations, and solving all kinds of equations, including differential equations. Okay, so now let me remind you also, so we talked about that if we have, if this here is a metric space, then a sequence in a metric space this is just a map, is a map from the natural numbers into X. So a sequence is like a map like this. And so usually the image of the n element, this we will typically denote again like this xn. So this is what a sequence is. A subsequence this is defined very similar to what we did on the real line. So a subsequence is the composition of f with an increasing, strictly increasing map G from the natural numbers into N, and then the sequence is then where you apply first G, and then you apply F. Right? So this gives you, when you first apply G, then it gives you another natural number, and so this thing here, the image of this is then an element in X. Right? So that's a subsequence. And again, this will strictly increasing guarantee you that the elements appear in the same order. You're picking a selection of them, but they appear in the same order as in the original sequence. Okay. So sequences and subsequences make sense. We can then also talk about, and I know we talked about, but I just want to, because of the break, I just want to review quickly a few of the things we talked about right before the break. So one is that a convergent sequence in a metric space. So if you take, if this here is a metric space and xn is a sequence in x, xn, xd, sorry, then we say that xn converge to x if the following hold. that for all epsilon greater than 0, there exist capital N such that if little n is bigger or equal to capital N, then xn, the distance between xn and this limit, should be less than epsilon. Right? So that's an exact parallel to how we defined the limit of a sequence, or that a sequence is converging if it was a sequence in R. Right? And likewise, we can define a Cauchy sequence in a metric space. So we define a Cauchy sequence. A Cauchy sequence in a metric space XD. So this is a sequence, so that for all, so it is a sequence Xn such that for all epsilon greater than 0, there exist capital N such that if little n, m, and little n are bigger or equal to capital N, right? So remember that a Cauchy sequence means that the tail is bunching together. So this means that if you are sufficiently far out, then these elements xn and xm are epsilon close together. Right? So this is what it means for a sequence to be a Cauchy sequence. And so now we have this theorem, and I think I mentioned it before the break, but let's just quickly run through it because it's very short. So if you have, so if this is a metric space, then the theorem is that any convergent sequence is also a Cauchy sequence. And the proof is like this. So given epsilon, since xn is a convergent sequence, so you assume that xn is a convergent sequence, let's call the limit x. Since xn converges to x, this means that there exist capital N such that if little n is bigger or equal to capital N, then the distance between little n and x here, this distance here is less than, and then I use epsilon over 2. Right? And so this means that, therefore, if little m and little n are both bigger than capital N, then the distance between the two, these two elements here, well, by the triangle inequality, we have that this distance is less than if you go over the point x. So if you go from xn to x, and then from x to xm, like that, right? But each of these, because both of these, both little n and little m and little n are bigger than capital N, then both of these distances are bounded by epsilon over 2. And so you see that this thing here is smaller than epsilon, right? So this proved that in a metric space, any convergent sequence is also a Cauchy sequence. And we saw that, so we know that if the metric space is R with the usual Euclidean distance, then actually you also, and that was the Cauchy convergence theorem, so the Cauchy convergence theorem. So Cauchy convergence theorem, it said that if x comma d is R with the Euclidean distance, so I denote the Euclidean distance like this, then we also have, we have the converse. The converse. So i.e. that any Cauchy sequence is also convergent. Okay. Now we looked at a very simple example, and if I have time, I will talk about a little bit more interesting example. Otherwise, I'll talk about that next time. So if the metric space was R with a Euclidean distance, well, then we had a converse. But if the metric space was, say, so we looked at where the metric space was, so where x here, the set, was the interval from 0 to 1, and the distance here was just the usual Euclidean distance. Right? So then if you're looking at the sequence xn, 1 over n, this one here, this is a sequence in this space. It's a Cauchy sequence, but it doesn't converge in this space because 0 is not part of the space. Right? So this here is a Cauchy sequence. So this, you may say this is rather trivial example, not very interesting. I'll show you another example a little bit later or next time that is more interesting, but in some sense has some of the same feature, that the space is just not quite large enough. Okay, but it will seem more interesting. So this here is a Cauchy sequence that is not convergent. Okay. Right. So again, you know, the Cauchy. Right. Yeah. So this leads to the following. This leads to the following notion here. So this is the following definition of being Cauchy complete. So a space, so a metric space x comma d is Cauchy complete if every Cauchy sequence is convergent. Okay. Okay. So now let me define some. So if let me begin with extending some notions from R. So the first one I want to extend is what it means in a metric space. What is a ball? So we have here, so a metric ball. So we have a metric space. We have a point in the metric space. We have some r, which is a real number, positive real number. And then we define br of x here. This here is the set y in x, so that the distance from x to y is less than r, strictly less than r. Okay. And so this here is called the metric ball. This set here is called a metric ball, or just a ball. With radius r and center x. Okay. Now let me just sort of illustrate it. So a lot of the intuitions about metric spaces, but you have to be careful because sometimes that intuition fools you, just because metric spaces are allowed to be very general. But a lot of the intuition about metric spaces come from just thinking about things in Euclidean space. So when I'm talking about Euclidean space, I'm thinking mostly about it could be on the line. So in the case where x is r, or it could be in a plane where x is r2, or it could be where x is r3. And so in either of those three cases, the distance is the distance that you're used to, which is the Euclidean distance we talked about. And so in that case, if you take a point here, so just thinking about the example where, let's think about the example where x is r2, then a ball here, well, a usual ball is really just everything that is the distance r from x, right? So this is kind of what I defined over here, right? There's another thing, you could also look at some other sets. So imagine that you take a line in the plane, and you could look at, or maybe this could even be, it would look more interesting if I'm thinking about a line in R3. So imagine that this is now this is supposed to look like in R3, and then you could look at a line, and you could look at, instead of looking at a metric ball, you could look at a tubular neighborhood. So suppose you're looking, that's very similar to a ball. So a tubular neighborhood, let's say a R tubular neighborhood, this is where you have some positive number R, and you're looking at everything that has distance at most, or let's say strictly less than R from this line. So if you do that, that would look like a cylinder, where the boundary of the cylinder is not included because I require things to have distance strictly less than R. Right? This is like, this here would be a R tubular neighborhood of a line. So this is just to say that this sort of notion here of a ball, you could even have something more general. And both of these things, right, that you know well from Euclidean space, they make sense in just a general metric space, right? Line maybe doesn't make sense, right? Sometimes, often it does actually, but that's something more complicated. But you could just think about it as a subset, and then things that have distance strictly less than R to that subset. Okay, so right, so this is what it means for this is what a ball is, metric ball. Then there's the notion of a subset of a metric space being bounded. So a bounded subset. So this is another definition. bounded subset of a metric space so we have a metric space here, and we have A is a subset of, and we say that A is bounded if there exists X, an element in this metric space, and D is some positive real number, such that A here is contained in the ball of radius D centered at X. Right. Now, with this, so there's a few things like this that we'll see, for these things. The empty set, right? If you take X and you take the subset that has no element, that's the empty set, then the empty set is contained in everything, right? So actually the empty set would be bounded, okay? But it's not a particularly interesting example of a bounded set, right? And it may be that the whole metric space, right? It's possible that the whole metric space is bounded, right? If it was like an interval, right? If it was just an interval where both so suppose you have some interval from A to B, then this thing here is, if you think about the usual distance on that interval, then that's a bounded set. The whole set X is bounded. So in particular, any subset would also be bounded. Okay, so now let me just prove one theorem, one little lemma, that is another thing that generalizes from R, and that is that if you take a Cauchy sequence, so any Cauchy sequence is bounded. So let's prove this.